Okay, we're just going to do another kind of rapid example. It's a little bit similar to the problem we did before. This is another surface area calculation because just seeing a few examples of these help get the process more established in our minds, right? So this is the problem statement you could have. This is actually problem 4 from section 913 in the textbook. Right, you would say the following. This would be maybe all you would be given in a problem like this, right? It says find the surface area of the portion of the paraboloid z equals x squared plus y squared that is below the plane z equals 2. Okay, so that's enough to go on. Paraboloid is a superfluous word. We don't need to use that. We basically have a function z which defines a surface above the xy plane. These problems don't always have to be z as a function over the xy plane. It's just that we're used to saying things that way, and when we introduce this topic, we keep it that way. But you could have y as a function of xz, or x as a function over yz. It doesn't matter. Right? But here we have that. And then we have another. So the other thing about these questions, a lot of times they're framed as the intersection of these different curves. You have this curve and this plane and this octant, and x is greater than 0 and y is less than 4, whatever. All these different things that taken together define some surface. And honestly, usually the hardest part of the problem is figuring that out. Once you can draw it, then there's a little bit of a hurdle to convert it to a double integral, and then you're just doing it. So that's why we want to look at another one here. So the thing you would do here is you'd sketch it in some way, right? So if I wasn't sure what to do, so basically the paraboloid here, if you think about this, well, what does this look like? You just do things one at a time. You don't do them all at once. So z equals x squared plus y squared. Well, like I do with what does z equal when x and y are 0? Like that's the first thing. When x and y are 0, what's z? 0. Okay, so this thing starts here at the origin. Okay. Now, just leave x as 0 for a second and say, well, now how does z vary with y? Well, z equals y squared. Okay, well, this is a parabola. So as y goes positive, it gets up as a quadratic. As y is negative, it also goes up. So it looks like a parabola, right? Just a second order polynomial moving out. So this is z equals y squared, z equals y squared, okay, when x is 0. But when y is 0, z does the same thing. So yeah, you can see, this just rotates. This is just showing us a parabolic dish, right? It's just doing this, going out to infinity, right? Centered at z equals 0. Okay? You could add this, I could say z minus 1 equals x squared plus y squared. And that would just be this entire parabola raised by 1. That may seem counterintuitive, like but you go z minus 1 equals x squared plus y squared. That means z equals x squared plus y squared plus 1. So it's the previous shape we have here, you just lift it up. Okay? So you can shift these things around. There's no need to do that, but you could see that. So we have a bowl, a parabolic bowl. Now, like I said, it's an infinite surface, so something else has to limit this. We're automatically guaranteed to be z positive just by the definition here. Z is never negative for real x and y. So, okay, we don't have to say upper half plane or anything. That's defined by z. But we do have to put a top on this. And so the way the problem does that is below the plane z equals 2. So, okay, that's cool. So you just draw a horizontal plane off the top that defines the top of the bowl up at z equals 2. Okay. The problem could say paraboloid between z equals 0 and z equals 2. That would be redundant. But sometimes you see that said. Okay? You could cut it in half and say, I've got this paraboloid, I've got this, below the plane z equals 2, and for x greater than 0. Then you'd have another plane that was x greater than 0 that was on the zy plane that would just give you the front half of the bowl. So you can keep cutting the thing into pieces, right, to limit the integration. That's just what you could have. Now, the only other thing to grasp at that when we're sketching before we go and calculate this is, okay, so we know we're up at z equals 2, so what does that mean in terms of an area over which we're going to integrate? So how big is this thing? Well, clearly it's a circle, right? Because the intersection of the paraboloid with the horizontal surface is going to be a circle, right? And what is that circle? Well, that circle is described as, it'll be x squared plus y squared equals 2, right? Because this paraboloid is x squared plus y squared equals z. When z equals 2, we're at the endpoints here. So this is a circle, radius, square root 2, right? So that's why I put square root 2 here. That's the extent in the xy plane. And when we convert this to polar coordinates, r will go out from 0 to the square root of 2. Okay? So that's the region over which we're going to integrate, and now we're ready to execute the parts of this. It's pretty straightforward to do this. Okay? So what we do is we decide, okay, what is the surface? The surface is the bowl. Okay? And that surface is z equals x squared plus y squared. So that's the height function, that's the surface function whose area we're trying to calculate. So so we've got, z equals, we already had that, equals x squared plus y squared. So I need the partial of z with respect to x, which is 2x. I need the partial of z with respect to y, which is 2y. Okay. And so then I'm going to have this square root of 1 plus 2x squared plus 2y squared, right? That's what's going to be the integrand with the addition of r if we make it polar. This is just the partial of z with respect to x squared, partial of z with respect to y squared. Right, so this equals square root 1 plus, I hope this is obvious, 4x squared plus y squared. And if we think about polar right from the bat, this is going to be r squared. So this is going to be square root 1 plus 4r squared. That's the integrand that we're going to integrate over. Now we're going to integrate that integrand over the subregion on the bottom. So our surface area, okay, area surface, okay. I'm going to integrate in polar coordinates. I'm going to integrate this function. And I'm going to do it in polar coordinates. The key thing when you're thinking about integrating in polar coordinates, right, is not always the surface above it. It's the region over which you're integrating. So I've got this surface hanging out over this circular region. So that's what makes me want to do it polar. Even if this top function was just a plane that was just z equals x plus y or something, you still would probably want to do this in polar because I've got this circular region in whatever case. Okay? That's what's really defining this. So here's this, but I'm not done yet. I got to decide what are my limits in theta and r. So here I'm integrating this entire circle. So the limits on theta are 0 to 2 pi, and the limits on r are 0 to the square root 2. So just like a previous problem, this one's pretty simple. They separate right out. Okay, so this is going to be 2 pi, 0 to square root 2, right? 1, sorry. Make this, not that really matters, but 1 plus 4r squared, 1/2 r dr, right? Because nothing depends on theta here, nothing depends on theta here, so I can bring that integration out. Not always the case, but often. And the problem is simple enough. Yeah, so maybe I can just finish up. We're going to do a substitution. We're going to let u equal 1 plus 4r squared. So du is going to be 8r dr. So r dr equals 1 over 8 du. Okay, so then this area is 2 pi, and I'll say this is r equals 0, square root 2. Let's just get this. We have u to the 1/2. R dr is 1 over 8 du. Right? So, okay, so I can take that 1 over 8 out for a minute. And then we have this, so then we have u to the 3 over 2 divided by 3 over 2, right? At square root 2, r equals 0. Okay, that's cool. Right, so we'll just take that 2/3 out. So we got, yeah, so, sure, let's do it. Got here I had pi over 4. Now I got 2 over 3. And then I've got, I'll put the u back as 1 plus 4r squared. 1 plus 4r squared to the 3 over 2. Evaluated at r equals square root 2 and 0. Right. Okay. So far so good. So he's gonna work on this a little bit. So what's this? This is gonna be 2 pi over 6. Pi over 6. And then we're gonna have, okay, let's do the first bit here. 1 plus 4r squared square root 2, so that's gonna be 2 to the 3 over 2 minus 1. Okay, so that is pi over 6. Okay, and then we just go, all right, so the 1's and the, oh, okay, I was going to say, I was almost going to cancel the 1's here, but I forgot. This one's inside the 3 over 2. So I need to simplify this down. So this is 8, so this is 9. 9 to the 3 over 2. I know you can probably do this in your head, you're a little faster. 9 3 2, so that's 3 squared. So this just becomes 3 to the 3rd, right? To the 3rd power. So pi over 6. And this becomes 3 to the 3rd power, so it's 27 minus 1. So this becomes 26 pi over 3. Oops, what am I doing here? 26 pi over 6. So I could take a 2, so that should be 13 pi over, take a 2 out of both sides, so 13 pi over 3. Okay. That's our answer. Now, hard to make a ton of sense about that. I guess you might say, well, okay, first of all, that's our problem, right? We drew our surface, we found the intersections of the curves, we then converted this to a surface area integration via the partial derivatives and the square root operation. Then we had a double integration, we did it in polar coordinates, good. We got a final answer, okay, final answer, positive, okay, that's good. What's another thing we could say? Well, I mean, it's surely got to be bigger than the area of the circle of radius square root 2, and that is pi r squared, so that'd be 2 pi. So is it bigger than 2 pi? Yeah, it's bigger than 2 pi. It's about 4 pi, right? It's a little bit bigger. So it's about 2 times the surface area of the bottom circle. That makes sort of sense, right? You take this paraboloid up, it should have 2 times the area. Yeah, maybe, not sense. If it was 150 times the area, that would be strange. If it was 8% more than the area, that would be strange, right? So is it twice? Okay. So it feels about right in terms of making sense of this whole thing. Okay, so that's a second problem in surface area integration. We're going to move on from these now and move on to true surface integration. We're not just doing an area, we're doing some other function that varies over the surface, and we're going to sum that all up.